Hello, welcome to CSC 7013, Advanced Math for Computer Scientists. This is Brady Chen. This is Module 8, the second part of Finite Automata. Now, in this part, we're going to focus on the non-deterministic finite automata. And as I mentioned earlier, that we're going to divide these module into two parts, 8a and 8b. In first part of the module A8a, we are going to introduce the non-deterministic finite automata, and then we're going to provide some of the examples of non-deterministic finite automata. And then in module 8b, we're going to talk about these NFA further, and mainly we're going to talk about the difference between DFA and NFA. And then we're going to talk about some of the operations on languages. Remember the definition for the languages in the previous module. And then we're going to introduce the regular languages and some of the regular expressions. In the previous module, we learned that a finite automata has 5 tuples. The Q, which is the finite set of state, sigma, which is the alphabet of import symbols, and the Q0, the starting state, and also F, the set of accepting states, okay, and then the transition function. Now, the main difference between the deterministic finite automata, the DFA, and the non-deterministic finite automata, the NFA, is the transition function. Let's say for DFA, the transition function is defined as if we have a current state which is in the set of states. So let's say the current state is A, and we have a current import value from sigma, okay, and it could be 0 or could be 1, right? Let's say it's 0. Then the transition function going to decide what's the next state. Actually, you're going to uniquely determine what's the next state. Let's say B, or could be A, but not both. Okay, it's unique, it's uniquely determined. So in general, we can say for any state and any import value, the transition function can actually leads to next state. So this is all uniquely defined. Now for non-deterministic finite automata, we know that for any current state, now with or without import, the transition function can actually leads to the transition actually occurs, and it's going to lead to a next state. So it could be, there might be an import, okay? So it's going to lead to either next state A, or it's going to lead to next state B, or it can actually go to A and a B, or it can actually lead to nowhere. So in also the transition occurs even there's no import. We use epsilon to represent no import. And then it can also lead to maybe nowhere, or A, or B, or C, or A and a B, or A, B, and a C. So there's all this possibility, okay? So it's not uniquely, the destination is not uniquely defined. That's the non-deterministic finite automata. So when we write the delta, we're going to say if the current state is Q, and then if the current state import is 1 or 2 from sigma, or we use union epsilon from nowhere, no import, then you're going to lead to multiple possibility, and we're going to actually use 2 to the Q. Now I'm going to explain why it's 2 to the Q. Okay, so as we mentioned that the main difference between DFA and NFA is that for a particular import symbol, okay, the machine can move to any combinations of states or move to nowhere. So, in other words, the exact state to which the machine moves cannot be determined. That's the reason why we called non-deterministic finite automata. As we mentioned that, with the current state, A. Now, and the current import, 1. Then the machine can move to A itself, or the machine can move to B, or if there's another state C, the machine can move to C, or the combination of A, B, or the combination of A, C, or B, C, or A, B, C. There's all the possibility, or it can actually move to nowhere. Okay, doesn't move to anywhere, So that's the difference. Okay, now let's look at the examples on the right. Now we have a diagram here, and we have 3 states, right? So in that case, the Q is a set of 3 states, A, B, and a C. And we know that the B is the final state, which is accepting state, and A and the C are not. And so in this case, now let's see what's the difference between this diagram and any diagrams of deterministic finite automata. Now in this case, so if the current state is A, okay, then if the current import value is 0, then we find out that delta A and 0 may actually get you back to A, right? So the current state is A, and then with the import value 0, and it's going back to 0. See this arch? It's going back to A. Or with the current state A and the import 0, it could actually lead to the final state B. Okay? So there are potentially 2 possible states the machine gonna move to. Now let's take a look at another case. That now once the machine actually get into the state B, Okay. And then we find out if the import is 0, it still stays in B, right? If the import is 1, it still stays B. Okay. It's going nowhere. Okay. Now also we find out if the current state is A, then without any actual import value, it may actually goes to C. Or with the import value 1, it can also go to C. So everything's possible. Everything, which is the possible next state or states is determined by the diagram. And this diagram is more flexible than the deterministic finite automata, right? So let's take a look at the transition function in this case. What is the transition function? Honestly, we still call the transition function, but it's not really a function from math perspective. Okay, let's look at the transition function for this non-deterministic finite automata. Okay, now again, we're going to draw the table. So that's the delta, and then these are the states. Okay, and these are the import values. Okay, now let's say in this particular case, if the current state is A, and if the current import is epsilon, that means the current state is A and there's no import. Remember, epsilon basically means no import. Okay. Then what's the next state? With A and epsilon, we know that the eigenvalue goes to C, right? Fine, no problem. Now, if the current state is A and the import value is 0, now there are two possibilities. Okay, one, it stays in A. Two, it could goes to B, right? So the destination, there are two destinations in this case, with the current state A and the current import is 0. The transition function may move the machine to possibly the next state A and the next state B. Okay. You see that the answer is not unique. Okay. Now, if the current state is A, again, and the import is 1, then we find out, okay, these curve actually move back to A. So the result could be A. Again, here's 1, here's 1, here's 1. So it could be B or could be C. With current state A and the import value 1, the destination could be A, B, or C. Now let's take a look at the next state B. Okay. So if the current state is B, okay, and if the import is epsilon, so that means there's no import. The diagram doesn't show the epsilon, so that means it's leading to nowhere. Okay, or we can say, okay, if there's an epsilon, it's leading to nowhere. but we don't have to draw this. Okay. So phi basically means it's a empty state. It doesn't lead to any place. Now, if the current state B import is 1 or 0, sorry, and then it stays in B, right? That's very similar to all the previous diagram. If the current state is B and the import is 1, then it also stays in B. So that's uniquely determined. Okay. Now what about a C? If the current state is C, so then we know that if the import is epsilon, so then it actually lead the machine to B. This one, C plus the epsilon. Okay. And now if the current state is C, the import is 0, then you will find out there's a two possible destination. C combined with import 0, C combined with import 0. So you can potentially go to A or go to B. Okay, A and B. Now with C and 1, so if the current state is C and the import is 1, the diagram doesn't show this. Okay, so in deterministic finite automata, this is not correct, because with any state, you have to define what's the next state for any import value. Okay, now in this case, if we don't have an import value, 1, drawn in this diagram, that means the C combined with import value 1 goes to nowhere. Okay. So that's the transition function. So you can define the transition function using this. As I mentioned, technically, this transition function is not really a function from math perspective, because in math, we basically means that for any actually value, that the function can actually, the value of the function is uniquely identified. Okay, so let's discuss the transition delta for NFA even further. Okay, so we mentioned that's the main difference between the NFA and the DFA, right? So let's say, suppose we have a set of state Q, which contains 3 states, A, B, and C. Okay, then we know that for each state and the import, the machine can potentially go to any state, or go to nowhere, or go to the combination of these states. Okay, so that means, so if I have a current state A, 0, it may potentially go to nowhere, or A, B, C, or A and B, A and C, B and C, and A and B and C. All the possibility, Now, so how many actual potential destination the machine gonna move to? For a finite state machine of 3 states, A, B, and C. So we find out that's 1, 2, 3, 4, 5, 6, 7, 8. There are potentially 8 different destinations the machine can go. with the current state and the current import value. Now this same thing could happen for A and 1. It could also potentially go to all these 8 different destinations, different actually possibilities. Or A with no import, it can also go there. Or B with 0, B with 1, B with epsilon. It can potentially go to these 8 actually different state or states. So now this number is not really random number. It's 8. Now it is actually 2 to the 3. Now what's that 3? That 3 is the number of states. Okay. So for example, if we have another case, Q equals A, B, C, D. You have 4 cases, right? Then what's the potential destination? Going to nowhere, going to A, going to B, C, D, A, B, right? A, C, A, D, and then we just then B, C, B, D, or C, D. That's all the possible of 2 states combination. And then we have A, B, C, A, B, D, and B, C, D, right? And A, C, D. I hope I include everything. And that's all the possible 3 states combination. And then the 4 state combination, that's A, B, C, D. Now let's count how many of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's total of 16. What's 16? That's 2 to the 4. So that number 4 is the number of states. Now, you're probably going to see that, in general, if the number of states is n, so in this case n equals 3, and in this state n equals 4, right? Now, if for general n, then the machine can potentially go to 2 to the m possible combination of states. Okay. So this basically explains why the transition function for NFA is defined as Q times epsilon union, sigma union epsilon to 2 to the Q. It's actually 2 to the Q possible destinations. Okay. So that's the difference. It's very, very different, right? Now the other difference is that the NFA can move to next state without an import stream. So that means it can move with the import epsilon. So there's no import. Okay. Also, NFA can move to nowhere, none of the state in Q. So that we don't know where it goes, That's the phi. Okay, we use the notation phi. Okay, this one we use the notation epsilon for no import. So that's the transition delta for NFA. So let's take a look at the example. So let us build a NFA that accepts string that contains contains 0, 1 as a subword. Okay, now let's do that. Okay, so how can we build this non-deterministic finite automata? So suppose the current state is A. Okay. Now, if the input is 0, let's say, if the input is 0, then we can go to another state B. Okay, because this is going to actually lead us, one more closer to the, accepting state, right? Because it is 0, so it's actually, we just need to find a string that contains 0 and 1. So if the next string is 1, then they're going to lead us to another state C, which is accepting state. Now, so, however, this is a non-deterministic finite automata. So it's possible that we can, allow the next state to be 0 as well. Continue to stay in A, because we allowed, if the current input is 0, and then we stay in A, and the current state is 0, we stay in A, because it allows us to have, as many 0 as possible. And as far as next one is 1, then we go to the final state. Okay. And if its current state is 1, we can also allow it to actually stay in A. Okay. So now if the current state is B and input is 0, then we can actually let the machine move, stays in B. Okay. Now if it's in C, once actually we reach the accepting state, now it's just the same as the deterministic finite automata. If the input is 0 or 1, we stays in 0 or 1. Okay. So that's the finite automata, the non-deterministic finite automata. Okay. So what about if the current state is A, but there's no input? Then we don't have to define the destination. So that means it leads to nowhere. Okay. If it leads to nowhere, we don't have to include this in the machine. Okay, let's actually look at this diagram further, the previous example. So we have the diagram for this non-deterministic finite automata that accepts string that contains 0, 1 as a subword, right? Let's look at the transition function. So based on the diagram, we see that if the current state is A, if the input is epsilon, which means that there's no input, then the diagram doesn't show anything. So that means it leads nowhere. Now, if the current state is A and the input value is 0, then we know that with the current state A, the input value is 0, it could actually stays in A, right? Like this one shows, or could goes to B. And then for A and its input value 1, it only stays in A, right? Now for B, if the current state is B, then if the import is epsilon, it goes nowhere because the diagram doesn't show anything. And B and 0, so current state is B, import is 0, it stays in B. B and 1, current state is B, the import is 1. Then it leads to C, the final state. Okay, same thing with C. If the import is epsilon, then it goes to nowhere. And if the import is 0, it stays in C. Import is 1, stays in C. So that's the transition function. Now with that transition function, we know that for any current state and the import value, the destination could be A, or could be B, or could be both. So let's take a look at the example of the first string. So let's check that how does the machine accepts or rejects an import string. Let's take a look at the first import string. Okay. Now I can leave this to you to finish. Okay. Let's say the start state is A. Now what's the first import? 0, right? So with 0, A and 0, there are two possible destinations. A stays in A or goes to B. Right? That's the result. Now what's the next one? Next import is 0. Okay, now we're going to actually study the next import for each possible state. So if the current state is A, now the import is 0. We know that there are potentially two destinations, right? A and B. Now if the current state is B, because that's the other possibility from the previous import value, so that's the other possible destination. Now if the next actual import, the second import is 0, then for B and the 0, it goes to B. Right? It stays in B. Now, what's the next import value? 1, right? So now we need to look at the import for each possible state. If the current state is A, the import is 1. Now what does the transition function defines? If the current state is A, import is 1, and it stays in A, right? If the current state is B, import is 1, it goes to C, which is good, right? If the current state is B, import is 1, it goes to C, right? Now we're not done yet. We only have 3 import values, 0, 0, 1. Now we need actually another import 1. So then we need to think about this for each of the possible state. A, 1, stays in A. C, 1, stays in C. C, 1, stays in C. Okay. Now the last import value, 0, right? So A0, there are two possible destinations, A and B. Now for C, 0, it stays in C, right? C0 stays in C. So actually C is accepting state. Okay. Now what's the conclusion? Okay, the conclusion is because for the sequence 0, 0, 1, 1, 0, you have potentially 4 destinations: A, B, C, and C. A is not accepting state. B is not, but C is, right? Another C is. So that means the machine gonna accept these string, because there's a possibility that the machine gonna move to the final state or accepting state. Actually, there are 2 possibilities, right? So that's accepting. Now, this is generally true, because if it's 0, 0, 1, 1, 0, so then it contains, 0, 1 as a subword, right? So there's a subword as 0, 1. So the result actually shows, yes, this is accepting. The machine gonna accept these string. Now let's take a look at another one. 1, 1, 0. We know that by looking at the string, there's no substring 0, 1. Now let's see how the machine actually takes. So let me find another space here. Let's say the start state is A. Now the first import value is 1, right? If the import value is 1, it stays in A, right? Based on this diagram, stays in A. And then the next one is also 1. Okay, it stays in A. And then the next one is 0. The last one is 0. So it could be in A, could be in B, based on the transition function. If it's A and the import is 0, then it could be A and a B. Now that's the last one. Okay, so A is not accepting state, B is not accepting state. So there's, look at all the possible destination. None of these is in the final state or the accepting state. So we rejected that string. Okay, so this is actually a very good one. Now, if we look at these, the diagram of NFA, we will find out that the answer for the NFA is not unique. So that means we can find another non-deterministic finite automata, which is different from this one, and actually it's going to do the same job. It's going to accept the strings that contain 0, 1 as a subword. So the answer for non-deterministic finite automata is not unique. Just let you know. That's just one of the answer. Okay, you can find another one which also gonna do the job. Let's look at another example. So let us build a NFA for language L1, which is the set of all strings over sigma, which contains 2 symbols, 0 and 1, that start with 1. Okay, so let's build this. You start from the state A. Okay, so then if the import is 1, then that means you actually start with import 1. So that means no matter what's the import after this string gonna be accepted, right? Because it's already started with 1. Okay, so very simple. Start with 1. Okay, now afterwards, it doesn't matter whether the follow-up string, what's the value of the follow-up string is, 0 or 1. It's always gonna stay in the accepting state. Okay, now for the deterministic finite automata, we have to define the import 0, right? Because you cannot skip any of the import value. You have to, for the current state A, you have to define the destination for any import value. So now for non-deterministic finite automata, you don't have to do this. You only say, okay, if the import is 1, we go to accepting state, and if for import 0, we could go to nowhere. Now, from this perspective, the non-deterministic finite automata is much simpler. If we try to define this machine. Oh, I'm sorry. In this case, this is n, non-deterministic finite automata. Okay, it's not deterministic. Now let's see how this actually works. Okay. Okay, so let's define the transition function for the non-deterministic finite automata. So if the current state is A, and if there's no import, then it's not defined in the diagram, so it goes to nowhere. If the current state is A, and the import is 0, goes to nowhere. And if the current state is A, and import is 1, it goes to B, which is the final state. And then for B, if there's no import, goes nowhere. If there's a import 0, stays in B. Import 1 stays in B. Pretty simple, right? It's much simpler than the deterministic finite automata that does the same thing. Okay. So let's take a look at how the machine accept or reject the string. Okay, let's take a look at these 3 examples, and I'm going to do the first 2. Okay, so let's say the first string 0, 1, 0. The starting state is A. The import is 0. Now, if the starting state is A, import is 0, it goes to nowhere. So it's lost. Okay, so it doesn't matter what's the next follow-up import. It just goes nowhere. So we'll reject this one. Now let's take a look at the second one. Okay, 1, 1, 0. Starting state is A. If we go to 1, if the import is 1, you're going to go to B, which is accepting state. But we're not going to stop here because there's a more import. The next import is 1. So the current start state is B. Import is 1. It stays in B, right? And then what's the next state import? 0, right? If the current state is B, import is 0, it stays in B. So we accept this string. So you can actually check the next string to see whether these non-deterministic finite automata can accept this string or not. And that's pretty much all for module 8A.